Welcome to lecture 16. In our previous sessions, we established the qualitative physical pathways of the Jablonski diagram. Today, we move one step further. We now quantify these competing processes. In any laboratory setting, we need a reliable mathematical metric to describe how efficiently a material emits light. This metric is called quantum efficiency, also known as a quantum yield. Physically, quantum yield is defined as the ratio of number of luminescing molecules to the total number of initially excited molecules. Highly fluorescent molecules such as fluorescence can approach a quantum yield of 1. This value is called unity, which means every absorbed photon produces an emitted photon. Conversely, non-fluorescent species approach a yield of 0 because radiation-less deactivation completely dominates. The overall efficiency is governed by the rate equation as shown here. Here, Kf is the fluorescent rate constant. The denominator represents all competing pathways, which includes Ki, that is intersystem crossing, Kec, that is external conversion, Kic, that is internal conversion, Kpd, that is pre-dissociation, Kd, that is dissociation. From a physics perspective, any factor that increases Kf while reducing non-radiative rates will strongly enhance fluorescence. To predict high quantum efficiency, we must use molecular orbital theory. In molecular orbital theory, sigma, pi and n represents different electronic orbitals. The asterisk, that is star, indicates an antibonding orbital. Sigma and pi are the bonding orbitals, whereas n is the non-bonding orbitals or lone pairs, whereas sigma star and pi star lie at significantly higher energies. Now consider transition types. Pi to pi star transitions having very strong absorption, larger molar absorptivity, highly probable fluorescence. These transitions require lower excitation energy, so they appear in the longer wavelength visible region. In contrast, sigma to sigma star transitions require extremely high energy. Another possibility is that n to pi star transitions, these can produce fluorescence or phosphorescence, but orbital overlap is weaker, so transition probability is much lower. Let us examine the energy limits of fluorescence. Experimental evidence shows fluorescence rarely occurs below about 250 nanometers. Why? Because photons near 200 nanometers carry enormous energy, about 140 kilocalories per mole. This energy often exceeds bond dissociation energy. Instead of emitting light, the molecule simply breaks apart. Therefore, sigma to sigma star transitions almost never produce fluorescence. The molecule destroys itself first. Most fluorescence therefore arises from pi to pi star and n to pi star transitions. After absorption, rapid vibrational relaxation occurs. The molecule quickly reaches the lowest vibrational level of the excited electronic state. From this stable position, fluorescence emission occurs as the electron returns to vibrational levels of the ground state. Now we compare transition efficiencies. Pi to pi star transitions generally show much higher quantum yield than n to pi star transitions. Why? Because molar absorptivity is 100 to 1000 times larger. A higher absorptivity means higher transition probability. This produces a very short excited state lifetime, 10 raised to minus 7 to 10 raised to minus 9 seconds. In contrast, n to pi star lifetimes are longer, 10 raised to minus 5 to 10 raised to minus 7 seconds. A shorter lifetimes means less time for non-radiative decay, therefore higher fluorescence efficiency. Interestingly, phosphorescence often becomes efficient for n to pi star triplet states. Intersystem crossing is more probable because the energy gap between singlet and triplet state is smaller. This favors delayed phosphorescent emission. Now we examine the instruments fluorometers and spectrofluorometers. Let us trace the optical path. A broad spectrum radiation source is generated first. The beam is split into two paths. The primary beam passes through an excitation wavelength selector, becoming monochromatic, then strikes the sample cuvette. The sample absorbs light and emits fluorescence. This emission is collected, passes through an emission wavelength selector, and reaches the main detector. Simultaneously, a reference beam travels through a beam attenuator, reducing its intensity before reaching a reference detector. Electronics then calculate fluorescence intensity divided by reference intensity. This ratio removes source intensity fluctuations, ensuring stable quantum yield measurements. Luminescence instruments include radiation source, wavelength selectors, and sensitive photodetectors. However, their measurement geometry is completely different from usable absorption systems. Most import instruments use right angle detection geometry. The detector is placed at 90 degrees to the excitation beam. This geometry minimizes excitation light interference, reduces scattering signals, isolates weak fluorescence. Instruments types differ by wavelength selection. Basic fluorometers use optical filters, cheaper but less precise. Advanced spectrofluorometers use grating monochromators in both excitation and emission paths. These dual monochromator systems enables continuous excitation spectra, continuous emission spectra, and a complete view of the material's energy structure. Thank you.